Hello, my name is Constantine. I'm a NIM developer at IFT, which is more widely known under the brand of Status. And in this talk, I will tell you about intops, which is a NIM package that is a collection of arithmetic primitives for integers. And I'm going to tell you why it was created, why it exists in the first place, and how to use it, and how it's structured internally. But first, again, what is ops? So it's an in package, as I already said, and it is a collection of operations for 64 and 32-bit integers, signed and unsigned flavors of those. Each operation that it offers is available in multiple flavors. For example, for addition, you could have saturating addition, overflowing addition, carrying addition. For the same applies to subtraction, division, multiplication, and so on. And I guess the most important feature of this library is that it implements, like it ships multiple implementations for each operation, and it tries to offer the user the most optimal, the most performant version for their operating system, CPU architecture, C compiler version. So it basically tries to understand what the best implementation for your situation is and offer it. While at the same time, you as a developer can just pick the implementation that you're interested in and use it in your project. So why was it created in the first place? I mean, we're talking about basically adding things, adding integer numbers. Doesn't that already exist in the name standard library? The answer is yes, it does exist in the standard library, of course. But the problem is that addition and subtraction, while appear very simple, really are not. I mean, there are many ways you can do that in modern on modern computers. Just because you have many different kinds of computers, you have different kinds of operating systems. So basically, for each operation, you have multiple ways of doing that, and those ways are very different in how performant they are under different circumstances. So the need to get a manageable collection of those implementations, that actually arises from two places. Well, first, the problem was stated in IFT, like within IFT projects. The problem is that our projects do use big integers here and there, and historically, the projects that would rely on big arithmetics would implement those arithmetic primitives internally. So you would have a library like stint, which does arithmetic for arbitrarily sized integers, and it used to have its own integer arithmetic implementation, which was optimized for various operating systems and so on. But there was no single reusable, manageable, documented package that everyone could use within IFT. Well, the other problem is, like, the other reason for this package is it does not have anything to do with IFT. It just comes from the fact that we're not living in a perfect world. So in a perfect world, like perfect programmers would create perfect NIM code, which, because the perfect NIM compiler would be absolutely optimized with no bugs, would produce the perfect C code, which would then in turn be transformed into a perfect assembly code by a perfect C compiler, which it does not. We would not see that in our real world, because in the real world we have multiple versions of C compilers that are released from time to time, the new ones. We also have new CPU architectures. Surprisingly, I mean, we have ARMs now, which are available in multiple versions. We also have different operating systems, and actually keeping up with all this like huge growing zoo is not a trivial task. And if we were to fix that within nim stdlib boundaries, that would mean that we would just have to slow down the standard library development, or we would have to compromise on uh, providing the most optimal solutions here and now for the particular user that is using the primitives right now. So basically, moving it to external package is the right way to go because it just allows for better maintainability. So now that we know why you would use intops, how would you use it? It's very simple. First, you install it like any other nim package. You can either install it with Nimble or you can just add it to your requirements. And then you can simply import it. You import intops and voila, you have all your operations available to you. You can also import just a subset of operations. If you're only interested in subtraction, you would import intops ops sub, and all the subtractions will be available to you. Also, if you are a developer that knows what they need and you want to surgically apply a particular implementation of a particular operation in your project, and you know what you're doing, we're not going to stop you. You can import intops impl and then followed by the specific implementation that you're interested in, and basically run call an operation implementation from this specific module. In this case, this example, we're calling the GCC intrinsics version of carrying addition. All that is documented, of course, so the links are on the screen. You can always find them. Here's a quick hand-drawn diagram, because I love hand-drawn diagrams. They have a certain soul to them, which explains, again, visually how that works. So you as a user, you would call intops. Intops module is an entry point for the API, and that would import all the operations from the intops module, which consists of specific operation families. And then when you call a specific operation, that would go to implementation submodule and find an implementation for this operation in the implementation that is required in this particular environment. And of course, you can jump straight to an operation family that you're interested in, or you can circumvent the entire interface and just import the implementation that you want. Now, let me talk a little bit about how this package is constructed and how it's done. Intops is modular and extensible from the start. It was pretty clear early on that if we're going to be hitting a moving target and like providing performance library is like shooting a moving target. So we will have to make it modular and easy to add new stuff to, and also to fix existing issues. So this is why it's split into three like large chunks. The first one is called dispatchers. Dispatchers is basically a very primitive, very short, brief nim code, which is nothing but when branches. So the sole purpose of a dispatcher is to decide which implementation to call for this specific operation, which means that each operation has its own dispatcher, and when you import intops, you're basically just importing dispatchers. It was obvious, again, early on that we have to allow every operation to decide which of its implementation are the best and implement its own logic, because there are no universal right and wrong answers when it comes to technology for implementing operations. So you cannot say that assembly is universally better than C, or like calling an intrinsic is universally worse than implementing a function in pure C. So each operation has to have its own, or at least be able to define its own logic. The second big chunk is implementations. It's a separate module that is grouped by the technology that is an underlying for its implementation. So we have like pure submodule, inline C submodule, inline ASM submodule, and some submodules are further divided into flavors. So for example, we have uh, like ARM64 assembly, and we have x86 assembly. And there's also the third chunk, which is called constants. And this is just a collection of compilation time available constants used by dispatchers to decide which implementation to call. Here's an example of what a typical dispatcher can look like. So this is a real example from the repository. I just removed the comments, but it's basically it. So you can see it's very it's not very long, and it's very obvious. I mean, it's really obvious what's happening here. So at first we check if this computation is needed at compile time. So the NimVM check does specifically that. And if it is, then we're basically restricted to using pure Nim implementation. That's it. However, if we're calculating stuff at runtime, we have a certain freedom of choice. Now, if it's a GCC compatible compiler, so GCC or LLVM, and using intrinsics is not forbidden by compilation flag, then we just use that. We use intrinsics. If intrinsics are forbidden, but we are on a CPU ARM64 architecture, then we can use inline assembly. And if inline assembly is forbidden with a compilation flag, or we're not on an ARM64 processor, then we just fall back to the universal fallback, which is pure Nim implementation. Our library is 100% test covered and 100% benchmark covered. And this is not all of it. The really cool thing is that our benchmarks are published online. They're available, like publicly available, so everyone can go to venture.dev and compare themselves which implementation is the fastest for each operation, and actually compare it to the logic that we've coded in a dispatcher. So maybe we're using the wrong logic. Maybe something should be prioritized instead of something else. So this is really cool that it's all transparent, and when you make a modification in the code, you can immediately see the impact it has on the entire library. Who uses intops right now? Well, as far as I know, and I cannot know for sure, but internally in AFT, intops is used by Stint, which used to have its own implementation of arithmetic primitives. It's used in bncurve library, and it's used in Nimbus, like two flavors of Nimbus, because both of those depend on Stint and bncurve, and therefore they are now proxy consumers of intops. Well, that's it from me. I'll be happy to answer all your questions on Discord or in the comment section. Issues and contributions are very welcome. We have a contributors guide on the website for intops. Feel free to create new issues and send PRs. Thank you for your attention.